Today, Gao Shuyang gives us a talk entitled Affine Diminishing Errors. Thank you, Gao, for accepting this invitation, and we listen to you for 45 minutes. Hello, Shank. Sorry.
Oh, okay. Shall I start?
Yes, you can start, please. Yes.
Okay, thank you so much, Professor Agash, for the introduction. So it's my great pleasure to be here to present this project. This is a joint work with my advisor, Dr. Mahmoud. And the idea of this project is to study a class of two-color affine Earth models. And the evolution of this process is based on drawing a sample of multiset at each discrete time step. So, and another feature for this class is that at each time step, we reduce a part of the population so that the overall population diminishes over time. And we will study the process of this diminishing. So we will start by providing an overview of the classic Earth models, just in case that we have audiences that are not particularly in the field of Earth models. And then we discuss the generalization of Earths from drawing a single ball at each time step to drawing a multi-set. And we will show some of the properties of this class, and then we discuss the class which we will study, that is the class of affine diminishing Earths. We will present the theorems that we obtain for this class, and then apply this class to model facts of trading strategies in the stock market. So that's is as a plan for today's talk. And so as a very brief introduction, in a classic polyar Earth, we have two colors of balls, and so we have two random variables, Wn and Bn, to mark the evolution of the process. So we have Wn, which is the number of white balls in the Earth after n draws, and Bn, number of blue balls in the Earth after n draws. So in a classic polyar Earth, at each step, we sample a single ball and observe the color, and then we execute the predetermined replacement rules. So the replacement rules are captured in this matrix, which is given as matrix 1. And so in the matrix, W and B, W here represents white and B here represents blue. So the column indices of this matrix are colors of balls in the scheme, and the row indices are the possible compositions of the sample. So pretty straightforward. The matrix is saying that if we have a white sample, we will add A white and B blue balls into the Earth, and if we have a blue sample, we will add C white and D blue. So for a classic polyar Earth and most of further generalizations of this class, we usually impose the balance condition so that the row sum of this matrix is a fixed constant K. And this K we call the balance factor. So by the balance condition, we have that Tn, which is the total number of balls in the Earth at time n. This is deterministic, which means that we only need to analyze the behavior of one color to determine the behavior of the other. So for this class of problems, the interest is usually in analyzing the asymptotic composition of the Earth process. So so just a very simple numerical example to show the path dependent feature for a classic polyar Earth. So suppose we start with 2 white and 3 blue balls in the Earth. So at our initial attempt, we have 2/5 probability to sample a white. And if we're on the white path, we will add 1 white and 3 blues into the urn, so that given that we are on the white path, our probability of sample of white in our second attempt will be 3 nines. And similarly, if we're on the blue path, we will execute the second row of the replacement matrix by adding 2 white balls into the urn, which makes our probability of sampling a white at our second attempt 4 sevens. So by this very simple step, we see that the path-dependent feature makes the problem very interesting, so that as we're repeating the sampling and replacing procedure, the number of passes in the sample space increases, which adds the complexity of the problem and also makes this class of problem very interesting. So show a few very well-known schemes for classic poly urns just to illustrate the variety of results we can get for poly urns. So we have the iron-fast urn where the constant row sum balance factor is 0. And for this one, we have that the binomial distribution is the stationary distribution of the process. And we say that in the binomial distribution, we have the initial number, which is the starting, the number that we started with. This is a parameter in the distribution. And we have the Pauli-Eigenberger urn, where the Y proportion converges in distribution to a continuous beta limit. And in this distribution, we also have the initial composition as the parameters. And we have the Friedman urn and the Bacci-Paul urn, where we have under some regularity conditions have a normal distribution as the limiting distribution. And we see that in this type of urns, the initial composition will not be shown in the meaning that whenever we start with, the process will forget the beginning. So from these few examples, we see that for poly urns, we can have path-dependent equilibrium, and we also can have path-independent equilibrium, which is determined by the replacement rules. So later on, a broad class of generalizations has been developed on classic poly urns, including a generalization from 2-color schemes to a scheme of multi-colors up to an infinite number of colors, and a generalization from sampling a single ball at each step to sampling a multi-set, and a generalization from using a homogeneous replacement matrix to using a time-dependent replacement matrix. And also we have a generalization from taking a fixed sample size at each time step to allow the sample size to vary according to time, and so on, and other directions.
Yeah, 1 second.
Yeah.
What is K here?
K here is the balance factor, so it's the row sum.
Okay.
Okay. So, so in our project, we will consider the generalization from taking 1 ball at each time step to taking a multi-set of size general S. And so for a multiple drawing urn model, the dimension of the replacement matrix will be S plus 1 by 2. And the column indices of this matrix are still the colors of the balls in the scheme. We use white and blue, and the row indices are the sets that can appear in the sample, where the S row is the sample that contains I blue balls. For example, in matrix 2, so A0 and B0 are the number of white and blue balls we add into the urn if we have 0 blue balls in the sample, meaning that the sample is all white. So for this class, the balance condition is usually imposed so that this row sum is still this constant k. So for this class of multiple joint error models, we can formulate a stochastic recurrence on the number of white balls. So it's the number of white balls from the previous step plus the contribution of this round of sampling. And so for this stochastic recurrence, if we raise it to power r, we will readily see that if we formulate the expectation and higher moments for Wn, it will depend on even higher moments from the previous step, which means this type of recurrence will be very difficult or even impossible to solve. So in fact, we can prove that if we define Qn as the white proportion, which is Wn over Tn, so Tn is the total at time n. So if we define Qn as a white proportion, we can prove that the mth moment of Qn plus 1, this is a combination of the moments from the previous step, but the order will be from 0 to s plus m minus 1. So what this is saying is that, for example, if m is 1 and our sample size is 2, this says that if we have the expectation for Qn plus 1, it will depend on the second moment of Qn. So we see that this dependence on higher orders, and the coefficients for this recurrence is this CLs, and we see that the CLs have double sums inside, so these are non-trivial coefficients like to solve, to work with. And maybe it's more straightforward to see this in the matrix form. So if we write the moments of Qn plus 1 as a vector, we can have that this vector is linked to the 1 up to mth moments of the previous step by this AN matrix, and it's linked to the moments of Qn, or higher moments of Qn, all the way up to m plus s minus 1 by this Bn matrix. So as long as this Bn matrix has a non-zero coefficients, we have this structure of dependence on higher moments, which by far we are not able to get a solution or even extract the asymptotic moments from this system of equations. So this is actually the underlying reason that when we start to work on multiple joint diminishing errors, we choose only to consider this affine subclass. So for the affine subclass, so the idea of this affine structure was proposed by Professor Mahmoud and later on developed by Professor Kuba and Professor Mahmoud. So their work is on the class of two-color affine multiple joint error models with all positive replacement entries. So Professor Kuba and Professor Mahmoud, they have proved that if the replacement entries satisfy the equation given by this equation 4, if this condition is met, then we have that the expectation of Wj, this depends only on the expectation of Wj minus 1, not on higher moments. So the idea is that we choose the replacement entries carefully so that we will be able to break the dependence of on the higher orders. So actually, this condition is sufficient that not just for the mean. All the moments will only depend on the moments from the previous step up to that order, not on higher orders. So this affinity condition, so this is actually the starting point we have when we consider the class of diminishing errors. So let's introduce our class. So we start by considering a class of two-color affine multiple joint diminishing errors by having the following. So the replacement matrix is still S plus 1 by 2, which means at each time step, we take a sample of size fixed S. So this S is some positive integer. And we add or remove the balls according to the replacement rules. So in the replacement matrix, AK and BK for each K is the number of white and blue we add or remove upon drawing a sample with the K blue balls. So again, A0 and B0 are the numbers that we replace when we have 0 blue balls or white balls in the or white balls in the sample. So these entries can be negative, and for the diminishing feature, we specify that the replacement in the replacement matrix, the balance factor is some negative number. So we call it minus K. So the diminishing feature is guaranteed by imposing the negative condition on the balance factor. And so it's not necessarily that all the replacement entries in this matrix are negative, but it's just that we need a negative row sum, constant row sum for each row. And with the diminishing feature, another feature we will impose is the affine feature. So the affinity condition is imposed by requiring that the replacement entries follow the structure given by equation 5. And this condition is developed by Professor Kuba and Professor Mahmoud for the urn with all positive replacement entries. And upon checking, we find that this also work for diminishing urns. So with the condition given by equation 5, we will have that the moments of Wj will not depend on higher orders. So basically, this is the class that we will study. And for this class, because we have the diminishing feature, so which means we reduce the population at each time step. So we are guaranteed that there will be some time that the urn will be tenable, meaning that either we will not be able to draw the sample from the urn or will not be able to execute the replacement rules. So we only consider a range of tenability in which we can carry out the rules. So this range is guaranteed by having equation 6. So what's this saying? These are saying is that so the maximum reduction that we will have, this is bounded above by the initial numbers that we start with. So with this untenability feature, we say that the problem will only be interesting if we start the urn with a sufficiently large number of balls. So we start with a sufficiently large number of balls, and we will have a large range of tenability so that we will be able to do some analysis in this range. So we assume that we start with n balls in the urn for some large n, and we assume that a proportion alpha n plus some lower order term gn, these are white, and the rest are blue. So we have two variables wj and bj, which are functions of n. These are the number of white and blue balls we have after j draws, and because we impose the negative balance factor condition, we have that the total Tj. This is n minus kj, which is deterministic. So because this is deterministic, we only need to analyze the behavior for the white color. So when n is large, we will have, as it goes to infinity, we will have a large range of tenability, tenability range that we can analyze. And we find that we can have two distinct phases. The sublinear phase, where the number of jaws j, this is some hn, and this hn is actually a function that is of order lower or little o of n. And we have the linear phase, where the number of jaws j, this is a fraction of n plus some lower order term. And to do the analysis for affine diminishing ergs, we impose the some regularity condition. We assume that Gn, which is the lower order term for the white proportion, this is of little o of hn, which is the lower order term for the drawing process, and all these are of little o of n to 1/3. So actually, we can change this set of assumption, and if we have a different set of assumption, we can do the proofs very similarly. The results will be slightly different, but of the same form. So in the asymptotic analysis, we rely heavily on the Stirling approximation to the ratio of gamma functions, which is given by equation 7. And for our analysis of affine diminishing, we present the results in terms of this capital lambda function, and which we call the Erg index. We choose to use the Erg index parameterization for this class just because this parameterization will significantly make the results look simpler. So we notice that this Erg index in the work of Professor Kuba and Professor Mahmoud for two-color affine ergs with multiple drawing and with positive replacement entries. In that case, the range of this is from -1 to 1. But in our class, this can take any negative or positive value. And for example, we have the following three matrices. The left one, which is the well-known OK Corral erg, this has Erg index -1. And the middle scheme has Erg index of -2.4. And the right one has the Erg index of 2.4. So after our definition for the Erg index, our first step to do analysis for this class is to obtain the expectation and the second moment for Wj, which is the number of white after J draws. So for the expectation, we find that the representation of the expectation is dependent on the Erg index lambda. So when lambda is not 1, the expectation is given by equation 8. And when lambda is 1, the expectation of Wj is given by equation 9. And then for the second moment, we find that the second moment for Wj is given by equation 10. And we notice that this is not a closed form expression in the sense that we have a sum of I from 1 to j. And except for some very special designed cases, this sum usually we cannot summate like explicitly to get a closed form. So which means to evaluate the second moment, we need to do asymptotic analysis to get its asymptotics. And so our the next step in our analysis is to do the asymptotic expansion for the expectation and also for the variance under these two distinct phases, namely the sublinear phase and the linear phase. So when we are in the sublinear phase, when the number of jaw j is of lower order compared to n, which is a number of balls that we start with, we have that the expectation of Wj, this is asymptotically equivalent to alpha n. So this is very intuitive in the sense that if the number of jaws that we have is of lower order compared to n, then the possible number that we have deleted from the population, this is also neglectable compared to the very large number that we start with. And after we do the asymptotic expansion for the second moment, we readily have the asymptotic expansion for the variance, which is given by the bottom theorem. So we have that the variance of Wj, this is of order j. So j is a little o of n. And we see that the formulation for this variance is very beautiful in the sense that the variance will be maximized if alpha is a half, meaning that if we have approximately equal size of white and blue to start with, then the variance of the process will be maximized. And the variance will increase as we increase the sample size or as we increase the gap between the replacement entries. So the expansion for the sublinear phase is very pretty straightforward. So we will just show the results and skip the proofs. And for the linear phase, similarly, I define phi as 1 over 1 minus k theta. Under the regularity condition, we have the following asymptotic expansion for the expected number of white balls after j joules. So EWJ is given by this asymptotic form. And we see that in the linear range, the coefficient for n, this is not alpha anymore, which means if the number of jaws we have is a proportion of n, so it's of the same order as n, then we will lose a sufficiently large proportion of the white balls. So even not very straightforward, the coefficient of n, this function actually is a decreasing function of theta. So and after we obtain the asymptotic expansion for the second moment, we will have the asymptotic variance of Wj, which is of order n in the linear phase. And for this part, we will sketch a very brief proof. So we get the asymptotic expansion for the variance if we have the asymptotic expansion for the second moment. And so let's evaluate this second moment asymptotically. So the part that is a little bit complex is the part that with the summation from I to j, because we have EWI minus 1 inside the sum. So in most of the cases, this cannot be summed like in closed form, which for this part, our strategy is we write each I as some rho times n, so this is a proportion of n, and we transfer this sum for I from 1 to j to a continuous integration for O from 0 to theta, which will be asymptotically equivalent. So as preparations, first we do asymptotic expansion for all the factors inside the sum. We have the asymptotic expansion for EWI minus 1, expansion for beta I, and beta I and the expansion for psi I. And we also, as preparations, do a asymptotic expansion for psi G, and this factor with this square term. And after that, so we combine all the factors inside the sum and apply Euler-Maclaurin summation formula to evaluate each part inside the sum. And because the integration and the summation, they are asymptotically equivalent, we will get the asymptotics for the second moment. And then through this, we will obtain the asymptotic variance. So yeah, for the linear phase, after having the asymptotic expansions for the mean and the variance, our next step of the analysis is to get the limiting distribution of the process in the tenable ranges through Martingale central limit theorem. So first, we prove that for balanced affine diminishing errors, this calligraphic WJ, which we call CalJ, this is a center martingale with respect to the natural filtration, and where the scaling is by this GJ function given by equation 11. And the proof for this is very straightforward. It's just by checking the definitions of a martingale. And with this center martingale CalWJ, our next step is to prove the Martingale central limit theorems by the combination of conditional Lindenberg's condition and the conditional variance condition. So by calculating UG and VG, we are able to prove that in the sublinear phase, the scaled version of WJ, this converges in distribution to a normal limit. And the scaling in the sublinear phase is the square root of J. And for the linear phase, we have that the scale version WJ, this converges also to a normal distribution. Just the parameters for the linear phase, this is more complex. And the scaling for the linear phase is by square root of n. And these are basically the results that we have obtained so far for affine diminishing errors. And so after we have these results, so we try to apply the results that we have, try to model some of path-dependent processes in the stock market. So if we look at the figure, which is the level to market data that is available to a trader when we trade like a particular stock. So the left-hand side graph, this is actually just a plot of the right-hand side data. And on the right-hand side, we have a list of buying and selling orders at a certain particular prices. So these are actually the existing orders in the market for this particular stock. And on the right-hand side, the green side on the left, these are all buying orders. And the right side on the right, these are all selling orders. For example, on the first row, we have the size 16 to buy the stock at $13.45. So the unit of size in this is in lots. So one lot is just 100 shares. So if we look at level to market data, we see that at some prices, we have very large size of a particular stock. For example, if we look at the green side, So the buying orders, we have a size 521,000 to buy at a price 13.15. And if we look at the right-hand side, we have $2.2 million to buy $2.2 million size to buy at $14. So with this finding, we notice that if we model the buying size as white balls in the urn and model the selling size as blue balls in the urn, then we will have a sufficiently large amount of initial balls to start with, which satisfies the assumption for our affine diminishing class. So this is the start point of our application. So let's first go through some of related definitions. So we define market depth as the size of an order needed to move the market price by a given amount. So for example, if we go back to our data, so on the right-hand side, so since we have 2.2 million selling orders at price of 14, this means we need at least 2.2 million buying orders in order to move the price above $14. So if a market is very deep, meaning that the market depth is large, at a certain price, we will have a very large amount of existing orders, existing size of orders, so that we need a large amount of trading in order to break the current price, make the price move. So in the market, we have different types of orders. So a limit order is an order to buy or sell stock at a specific price or better. So if we go back to our data, so orders that are listed in level 2 market data are limit orders, because these are orders where the target price is specified. So if the buying price is lower or exactly equal to the target price, the order will be executed. And as opposed to a market order, so a market order is an order to buy or sell a security immediately. So a market order is guaranteed to be executed, but the execution price is not guaranteed. So the price is typically around the current market price, but not guaranteed. So with these definitions, so let's have a very simple scenario. So this is a simplified version of the data, just to make sense how our diminishing scheme will be used to model this path dependent process. So suppose at the price of 100, we have a buying size. So bid size is a buying size, ask is a selling size. So we have 2 million bid size, and at price 101, we have 1 million asking size. So we model the bid size as the number of white balls in the urn. So this is a W0, this is a 2 million, and similarly, ask size, we model it as the number of blue balls in the urn. So B0, what we start with is 1 million. So let T0, which is the total number of balls in the urn, let this represent the total number of existing size in the market at time 0. So T0 for this simplified version of data, this is 2 million plus 1 million, this is 3M. So let's define J as trading epochs. So at each J, we have an investor coming to the market and execute a market data of size K. So notice that these epochs, these are not necessarily equispaced. So And we assume the trading strategy to be that the trader will come into the market and choose buy or sell side with probability given by current strength of each side. So an investor comes in, and the investor, for example, for this data says that the buying versus the selling, this is a 2 to 1. So the trader will have probability 2/3 to be on the bid side, because the investor thinks that the bidding side, this is has more strength, so has more power. So it's more possible that the price of the stock will go up. So the investor will choose to be on the buy side. So if we define IG indicator J to be the indicator that the J's trading is a buying order, we have that the probability conditioning on the information from the previous step. This takes value 1 with the probability as the proportion of white balls from the previous step. So this means that the diminishing of the market depth, so the changing of the existing orders, which we call the market depth, this can be modeled by the following replacement matrix given by equation 12. So we have zeros on the diagonal and minus k on the off diagonal. For example, back to our data, if the investor, if at time 0, so at time 0 we have 2 million B size and 1 million S size. So if at if at time 1 we T1 we have if at time 1 we have investor coming into the market, and by observing the current market data, the investor will have a probability 1/3 to be on the selling side. So if the investor is on the selling side, the investor will place a market order of size K, and this size K, which we see as K balls into the urn, this will be paired with K buying orders, so that it will reduce the number of buying orders with amount K. So with probability 1/3, which is the white proportion, which 1/3, which is a blue proportion in the urn, we will reduce the buying size by K. So this is the second row of the replacement matrix. And if the investor sees this data, the investor will have probability 2/3 to be on the buying side. So if the investor is on the buying side, the investor will execute a market order of size K, but these orders are buying orders. And with these buying orders, these orders will be paired with K size of K selling orders, so that the number of blue balls in the urn will be reduced by amount K. So this is the first row of the replacement matrix. We reduce the number of blue ball by amount K. So with this formulation, we will use the results that we have obtained for affine diminishing urns, so that in the sublinear range and in the linear range, we will formulate the expansions for the expectation, the variance, and the limit distribution. And from these results, we see that the dynamics of WJ, which is the dynamic of the market depth, this is actually an interplay of different factors. So we have alpha in the formulas, which is representing the strength of buying and the selling side in the market. And we have K, which we can interpret as a factor that represents the liquidity in the market. And we have a factor J, which is number of draws, and this is a number of tradings that we have during a certain time period. And this we can interpret as the trading volume in the market. So actually the dynamics of WJ, this is a interplay of different factors. And if we look at the variance of WJ, we see that both in the sublinear phase and in the linear phase, the variance actually this is maximized when alpha is a half. I think this is very intuitive in the sense that if the buying strength and the selling strength, they are approximately equal in the market, then the variance of the market depth is maximized, which means that we are less certain which side of balls, which color of balls will be extinct first. So we are not sure if the direction of movement of the price will go up or down, which means if the variance of WJ is maximized, the variance of the stock price, this is also maximized. So of course, this is only a simplified version of data, and later on maybe we will make it more complex and to adapt to the real world data. So that's pretty much all our results for our fine diminishing errors. And I thank you very much for your time and attention. And any question is more than welcome. So thank you.
Thank you for you, Shuyang, for this nice and well-structured talk, and for these nice applications. It's the first time for me to have some application, give some connection between polio earnings and financial problems. Is a very nice applications. Are there some questions from the public, please? Are there some questions?
One question I have, maybe I didn't catch this particular notation. What is this phi that is in the linear range? That phi squared, phi?
Function that we define, we choose to define it just to simplify the representation of the results. So if we have this phi, the formula of the form of the formula will look nice. So it's it's 1 over 1 minus k times theta. So k is the balance factor. Theta is the proportion, the proportion that the number of jaws j we have between this j and n.
Okay, thank you. There's a wonderful talk, Shuyang. I'm going to look at this.
Thank you so much.
Is this paper published?
It's rejected, but we have submitted and it's rejected, and we will submit again.
Anyway, it's very interesting. I want to look at it. Okay.
Okay, we can share it with you, even if it's not published.
Yeah, the paper was rejected, and the referees, when they don't find anything real to attack a paper, they say, "What's the motivation?" So the referee said he doesn't see a motivation. Why would one consider a diminishing earn? And just left it at that. And that was, it was like left us in a bad position, I guess. Mm-hmm. I have a question for you, Shuyang.
Mm-hmm.
I did not quite catch why in the stock market application, why do the number of balls come down? It's like if you have a new investor, then W0 and B0 is the status of the market today, for example. Okay, so he comes and sees that there are 2 million, willing to buy and 1 million willing to sell, things like that. Then that person, that new investor, he will place an order.
Yes.
Why would it decrease either side?
Yes, because if the investor, for example, places a buying order of size K, then this order will be paired with a selling order and it will be executed. And after the execution, the existing selling order will be reduced by amount K.
I'm not sure I understand this pairing. Is it because he's buying it from someone?
So he is buying it at the current price.
So when someone buys a stock, someone else is selling a stock. That's what you're saying.
Right. They get paired.
Okay.
Yeah.
Who is that someone else? The financial institutions, the banks?
The other investors that have placed orders.
Okay.
Yeah.
I have a general question, Shuyang, please. Are there any connection between earn and normal earn and habitual earn by reversing the time? Understand me? Are there any connection between a diminishing earn and a normal earn by reversing the time?
That is actually a great question. So Professor Mahmoud and I, we think that this actually can be coupled with an increase in earn. Can be coupled with an increase in earn because for the original OK Corral paper, I think there is one strategy to solve the OK Corral earn by coupling it with Friedman's earn. So the idea, I think this is valid. It's just we haven't obtained the proof in that sense.
Well, one main difference will be all the forward going earns, like the growing earns, start from fixed conditions. We are starting from conditions that are asymptotic already. So while it might be possible, Rafiq, it just needs some new sharpening of what exists. You understand what I'm saying?
Mm-hmm.
Like the number of white balls at the beginning is n going to infinity.
Mm-hmm.
Yes.
Okay.
Mm-hmm.
So I am not sure that there are results in the literature of growing earns that deal with this.
Mm-hmm.
But as you said, it might be possible. There just needs some tweaking, some sharpening.
Okay. I have another question, not a precise question, but general question. Your diminishing earns stops any time, sometime. Okay, can be stops.
Yeah.
Okay.
Yeah.
Have you some results about the asymptotic distribution of the stopping time?
That's a great direction to work with that we haven't touched. But I think this is typically this is a well-studied problem for the single join diminishing earns. But for multi-join earns, I think this problem has not been touched. So we haven't, but we can try. It's a very nice problem to consider.
And your addition matrix is deterministic.
Yes.
The addition matrix can be
random. Can be random.
Yes, can be random or not. In your, if I change the matrix by balanced random matrix, balanced in means, in mean, I have the same results.
I think so. I think the results
can I have the same results?
I think so. I think we will have very similar results in the asymptotic mean, in the asymptotic variance, and also in the asymptotic limiting distribution. So I think the difference is that if we have random entries, then the possible maximum deletion will depend on the range for this random variable, which means our tenability range will change. Maybe it will be reduced significantly because there might be a path in the sample space that after very few number of draws, the process will extinct.
Okay, I think so that if I take a random matrix, which is independent of all the past, I have the same result because
Yes,
every time
yes.
use only the of the WG.
Yes,
WJ.
yes, yes. We use only actually the results are only based on the mean.
Are there other questions? Okay. Balaji, is a real pleasure to meet you today with us in this webinar.
Yeah, it was a real pleasure to meet you too. Yeah.
Thank you. Thank you again,
You should
Shuyang,
come
for
sometime
this
here.
nice talk.
You should visit.
Okay, thank you so much.
Sorry. Thank you
I'm saying
for
should
you.
visit.
Thank you for all. Thank you, Balaji, Sam.
Visit our university.
Okay.
Rafiq,
Sam, thank you, Nabil.
okay, it's
Yes.
our last webinar this year, and I wish you happy holidays and happy summer.
Thank you. Thank you.
Thank you so much.
See you
Bye.
Bye bye.
in September,
Inshallah.
Nabil.
I hope I can
Bye.
see you during the summer, Rafiq, in Tunis.
Okay. Okay, inshallah. Okay.
Okay.
See you. Thank you again,
Okay,
Shuyang.
thank
Bye
you.
bye.
Bye. Bye.